Take an initial point, x sub 0, and map it through this function to find a new location. If we feed that output back into the function as the next input, we can watch the sequence move toward a specific point on the plane. This behavior is governed by the Banach Fixed Point Theorem. It provides a constructive method for solving differential equations and large systems of linear equations by turning them into iterative calculations. We are deriving this theorem directly from the work of Erwin Kreyszig. To follow the proof, we assume the points exist within a metric space, where distances are defined, and that the space is complete. The theorem relies on the definition of a fixed point. If applying function t to point x returns x itself, the point is fixed. A function that shifts every point in one direction has no fixed points, while a rotation around a fixed origin has exactly one. Next, we define a contraction mapping. If we apply this function to any 2 points, the distance between their images must be less than or equal to a constant ratio, alpha, of their original distance. This ratio, alpha, must be strictly less than 1. By keeping the ratio strictly below 1, the function ensures that the images of any 2 points are closer together than the original points themselves. Because this compression happens at every step, the sequence cannot diverge. The formal theorem requires a complete metric space and a contraction. When these hold, it guarantees the existence of a unique fixed point and the convergence of our iterative sequence. We begin the proof by constructing the iterative sequence. We choose any starting point x0 and define each subsequent point by applying the function t to the point before it. To prove the sequence converges, we have to show it is Cauchy. We expand the distance between any 2 distant points in the sequence, xn and xm, by using the triangle inequality to sum the individual segments between every intermediate point. Because each segment is a step in a contraction mapping, we can pull out the constant ratio, alpha. This forms a geometric series. Since the ratio alpha is less than 1, this geometric series converges to a finite mathematical bound of 1 over 1 minus alpha. The sum of these distances resolves into a finite bound. This allows us to classify the iterative sequence as Cauchy. This is where completeness is required. While a Cauchy sequence always compresses, it only converges if the destination point actually exists in the space. Completeness ensures that the limit point, x, is an element we can work with. To confirm x is a fixed point, we measure the distance to its image, tx. By routing this distance through our sequence points, we find that as we move further down the sequence, the remaining distance drops to 0. Therefore, x must equal tx. Now, take a brief moment to prove that this fixed point is unique. Assume a second fixed point y exists. If we apply the contraction rule, the distance between x and y must be less than itself multiplied by alpha. Since alpha is less than 1, that distance can only be 0. To estimate the accuracy of our iterations, we use error bounds. The prior bound uses the first step's distance to predict how many total iterations we need, while the posterior bound uses the most recent step to calculate our current precision. The prior bound allows for planning computational resources before the process starts. The posterior bound provides a measure of accuracy as the data is generated. We can apply this to solving large systems of linear equations. Rather than using direct elimination, which can be computationally expensive for sparse systems, we rewrite the problem as an iterative process, x equals cx plus b. To ensure this process converges, the matrix C must act as a contraction. We verify this by examining the coefficients of each row. If the sum of the absolute values of the coefficients in every row is strictly less than 1, the mapping is a contraction. Under these conditions, Jacobi iteration is guaranteed to converge to the unique solution. With each iteration, the mapping forces every possible guess toward the center. The entire field of points contracts until the sequence identifies the single point that satisfies the equation. This demonstrates how the abstract definitions of functional analysis, like metric spaces and contraction mappings, form concrete tools for solving specific problems in differential modeling and linear algebra.